So good afternoon and welcome back to the heavy ion session. And this talk will be dedicated to heavy flavors. So it will give you an experimental perspective on the measurement of heavy flavors and what they convey us in heavy ion collisions. So the outline would be what are heavy flavors and why heavy flavors, and together we'll have very recent results from Rick. So as I've mentioned numerous times that we can create this deconfined phase of quarks and gluons in ultra-relativistic collisions, but the issue, and we would like to know its properties, but the issue with this is that these are very short-lived. So the time frame is of order of few Fermis, so it is not possible to really send any external probe and get information about the system. Okay. So since it becomes difficult, so it would be apt if we can use self-generated probes. That means which are there already in the system before that, and somehow we can access those probes to fetch information about the system. So we would like to have probes which were generated at the same time, or let's say before the system was formed, and somehow that probe enters into our detector system so that it studies the entire evolution of the system and then it gives us the information. So that would be really good for us. So let's see whether such probe exists or not. So how do we define a good probe, okay, to study this medium? So ideally, a probe produced early in the collision evolution so that it is there before the matter to be probed. So if it exists before the formation of QGP and somehow we can get that probe, then it will be good for us. And that probe should be such that it should be well understood in PP collisions or any basic collisions where we do not expect such a matter to be formed. And that should be slightly affected by the hadronic matter, and it should be strongly affected by the deconfined medium because we need this information. Suppose that probe is immune to the strong or the interacting QGP, then it won't give any information about this. So it should be interacting with the QGP so that it is strongly affected by the deconfined medium to give us some information. And how to calibrate that probe? So we should have systems or other probes which are not significantly affected by the medium. So if we find these characteristics in a probe, then it would be a good probe to really give us information about the system. So what are the probes which really satisfy, if not all, some of the conditions of a good probe? Those are mainly jets and heavy flavor because they are produced very early in the hard scattering processes. Okay. So then what are heavy flavors? So heavy flavors, as you all know, are charm and beauty quarks, and these are massive compared to your light flavors, and the masses are greater than lambda QCD, so their formation time is quite early. So you can calculate this, so they have extremely short formation time, and this formation time is, let's say, less than the formation time of QGP. So that means they are created very early in the collision process, so we expect them to pass, or we expect them to witness the entire history of evolution of the deconfined medium. So now what are the processes by which they are produced? So these are mainly flavor production, then gluon splitting and flavor excitation. So these are the processes which one can calculate in PQCD processes, and therefore they are well understood, or let's say PQCD can really give the cross section of their production. So far so good. So then what are the types of heavy flavors which we measure in experiments? So basically we have two broad classes. One is open heavy flavor. So those are normally called open charm and open beauty. And the second class is the quarkonia. Now when I say open flavor, so they have either one charm or beauty quark associated with a different, let's say, light flavor thing. So we have your D mesons, B mesons. So those are normally known as the open heavy flavor mesons. Then there are quarkonium, like you have a CC bar state or BB bar state, normal J psi or upsilon. Okay. Now if you see the production, or let's say compare the production, so most of the times we get light open flavor. Okay. And strange D mesons constitute a smaller part, and then we have this charmed lambda baryons, and we can see charmonium is the least. So if we see the entire production cross section, so charmonium production is quite less compared to the open charms. Now why heavy quarks? Because they are dominantly produced in very initial stages with large energy momentum transfer. So they are produced in very hard processes, and therefore they are produced very early in the collision, and their production is well described by PQCD. So we understand what is their production and what is the cross section. And their scattering cross sections are small compared to the light quarks. So once they travel through the medium, they really or if they hadronize, they really don't interact much with the environment, so they preserve the information. Also their numbers are conserved, and they're also sensitive to the medium properties during expansion. So they interact with the sea of deconfined quarks and gluons to give us information. So by virtue of these properties, they can be classified as one of the cleanest probes for early tomography. Now let's see what's the difference between a PP and normal AA production. So as you all know, so suppose we have two hadrons colliding to give this particles. So normally the cross section can be broken down into the PDF of the incoming quarks, and then the product platonic cross section, which is well described by PQCD, and there is their fragmentation into hadrons. Okay, this is a typical PP process which can be calculated or predicted by really convoluting all these factors. Okay, now suppose now replace this PP with AA production. So again you will have similar things, but the cause of worry is that if your AA production cross sections were similar to that of PP, that means if you can assume that AA collisions are like collisions between many, or you can assume AA collisions like collisions between many protons and neutrons. So there are no effects of QGP or something exotic which we are seeing. Then we can see that the production cross section will have this simple scaling. Okay, because the only thing which is differing between these systems is the number of binary collisions. In case of PP, it will be 1, while in AA, it will be many compared to PP. Okay, so this sort of scaling should be observed. Now, if any deviation is observed in this scaling, so that should be attributed to something different happening. So this hadronic cross section is the Parton spectrum, then energy loss distribution, and the fragmentation function. So why you study heavy flavors on anything in PP? Because they're useful test of the theory. You understand, let's say for heavy flavor, you understand the production, and also it provides a baseline for your heavy ion collisions. Now for heavy ion, why it's important? Because different interaction with the medium with respect to light quarks. So these are like powerful tool to investigate the medium properties in AA collisions. So let's see how do they interact. So passing partons, let's say you heavy quarks, while they traverse through the medium, they can lose energy via scatterings with partons, which is known as the collisional loss. And this is the mechanism which dominates at low energy. And then they can also have this gluon radiation. They can lose by gluon Bremsstrahlung, and that is significant in higher energy. So if your quark has passed through the medium, the energy will be less than what it has before, and this reduction in the parton's energy translate into a reduction in the average momentum of the produced hadron. So this is something that we do not observe, but this is something which we observe experimentally. We can measure the transverse momentum spectra. So because of this polar shape of the PT spectrum, a modest reduction, even if we have a small reduction in the parton energy, it produces a significant decrease in the hadron yield. Okay. And now there's also energy loss which depends upon the type of quarks, or let's say the flavor of the quark. So passing partons lose their energy through elastic scatterings and gluon radiation. This we know, but what does it depend on? So it depends on the color chart. So gluons will lose energy differently than light quarks, and they will lose energy differently than the heavy quarks. Then their quark mass, which is the dead cone effect, so which is important for, let's say, heavy quarks, because in this zone the radiation or the radiation loss is minimized. So that's the dead zone. Then there's the path length. So the length in the medium, if the like in central collisions where the medium is more dense, if the quarks passes through the medium formed in central collisions, it will lose more energy compared to peripheral collisions where the medium length is less. Now let's see some open heavy flavor which are normally measured in experiments. So what you see, this is their mass and this is their C tau. So you can see that it is of the order of hundreds of micrometer. So therefore the vertex or the decay vertex is displaced from the primary vertex. This is important because this introduces an important, let's say, topological cut when we do the identification of these heavy flavors. And these are the decay channels. So you can measure depending upon what is accessible to your detectors, you can, and also the branching ratio, you can access the decay daughters and reconstruct your, let's say, heavy flavor mesons. Okay. So before going to the experimental results, it is important to know that these particles are, let's say, not very easy to reconstruct. You need to know the techniques, and also you need to have the relevant detectors in place to give you that information. Okay. So most of the particles studied in particle physics, as we know, are unstable and they decay within a finite lifetime. So you have to reconstruct those particles to get information about them, and the probability of decay depends on the lifetime of the particle. This is something which we know, and these are the lifetime and mass and the C tau decay length, everything for some known particles. And let's see, by virtue of the fact that a particle decays, its mass or energy cannot be determined with infinite precision. This is something which we know, and this constraint is given by the Heisenberg's principle, and therefore we have a spread in this invariant mass spectrum, and the particles can also decay in many ways. So each of the decay modes have a certain relative probability, which we know as the branching fraction. So it's better to use decays if your detector can decay, which have higher branching fraction, so that the probability of reconstructing that particle increases. Okay. So what are the elementary observables, or let's say what are the kinematic observables which you need to reconstruct your heavy flavors? Most important are momentum, time of flight, energy loss, particle identification, and invariant mass reconstruction. Because these particles decay, so you should be able to identify the decay daughters. You should also know the energy and momentum of the particle to get the invariant mass. Okay. So these are the typical momentum definition which you know from your physics classes, but how do we measure that in experiments? So normally we know that when we used to study in our textbooks, the way you measure the momentum is via your spectrometer with a constant magnetic field. So we know that charged particles passing through them will be deflected by the Lorentz force, and then you get the centripetal force, equate them, and you get the momentum. Now, similar thing is also done in high energy detectors. So B is the magnetic field is determined the, let's say, construction or operation of the spectrometer. In our case, it's the detector. So this R must be measured for each particle. It's the radius of the helical path. And the trajectory of the charged particle through detectors are sensitive to particle energy loss and are capable of measuring the location of energy deposition. So once you measure the radius, you can get the momentum information. Okay. So then the next important thing is the particle identification, because let's say your D0 meson decays into a pion and kaon. So you should be able to tell from the tracks that which is a pion and a proton. So you have specific detectors for them. Let's say this is the energy loss spectrum obtained from a time projection chamber, which utilizes the let's say Coulombic energy loss of the charged particles while they traverse through matter. So you can know that you can quantify, let's say parameterize this loss by your Bethe block function, and so you have a different distribution for different particles. By utilizing this, these are all tracks. So by utilizing this information, you can tell whether your particle is a pion, kaon, or proton, but each detector has its own limitations, so you will be only able to identify in a certain acceptance of the detector. And then you have to, and if you are fortunate, okay, enough, then you will have a complementary detector which will provide more information so that you can really take both the information and make your identification. Then this is the invariant mass which we do for all the decay because you will only get tracks, you won't get the D meson or J psi meson. You are not going to get that. So you have to reconstruct that particle from the invariant mass distribution. And this is, everyone knows, this is a Lorentz invariant quantity. But if you see in a heavy ion environment where you have thousands of particles getting produced, so you really can't know which is the decay daughter of a certain particle of your choice. So there's a high likelihood that, because once you combine particles, maybe you are identifying, let's say a D0 decays into a pion and kaon, so there will be several pions and kaons, and most of them won't be coming from the D0 decay. But that information is not there with you, so you, at your end, you can at best utilize some of the topological cuts, but then you have to combine the random, you have to take random combination of each and every pair which really comes after your filtration cuts. So there's a large likelihood of pairing together tracks that do not actually belong together or that do not come from the decay of the particle of your interest. So in that case, although you will get a signal in the invariant mass region of your interest, but that will be also corrupted by a significant background. So you'll have to resort to good background subtraction method, so you can get the, let's say, near correct yield of your particle of interest. Now let's say this is a heavy quark. As you know that you'll have a displaced vertex, the C tau is large. So after traveling a distance of C tau, that heavy quark will decay to its daughters. So let's say you have a B quark, so and it decays into, let's say, leptonic channel. The cross section is, let's say, 10% sample. If you see, the sample is 10%, or let's say order of the 10% of the total B cross section. Now if you want to select one specific channel from that, let's say dilepton channel only, so then it will have, you see how the cross section decreases. And if you want to be more exclusive, then you want to tag a non-prom J psi and then want to reconstruct a B meson, then it is even more difficult. So just this is an example to show that you require flexible trigger systems, good identification of leptons, then secondary vertex reconstruction and jet reconstruction. So you need to know all these tools to really reconstruct your heavy flavors. So for D and B, you have It's the most direct measurement of open heavy flavor, but complicated since it requires good capability in the decay vortex reconstruction, and in gold-gold collisions, or let's say heavy ion, it suffers from a large combinatorial background. So if you want them to, let's say, reconstruct from, let's say, so if you want to fetch the information from single leptons, then although branching ratio is large compared to the hadronic channel, but it requires an accurate knowledge of the photonic and non-photonic background sources, which and the understanding of those background sources is required to really understand or to get the correct spectrum of the heavy flavor. And if you want to do the measurement with muonic channel, you should accurately measure the let's say distance of closest approach to separate mu from charm decay from pion or kaon decay. So this is the example of invariant mass of DS meson reconstruction, which is quite difficult, or it's a process that requires a lot of statistics to get observed. Let's skip this. So we discussed what are the tools which we need to, let's say, reconstruct our heavy flavors. Now let's see what do we need, what are we exactly measuring for these mesons to extract the properties of the medium. So let's start from the initial stages. As I mentioned, we can explore initial state with flow coefficients. So in the first half of today's lecture, I mentioned something about non-elliptic flow. So if there is a non-central heavy ion collision where the overlap shape is of, let's say, is of almond, or we can say an ellipsoid, then you can see the pressure gradient along the minor axis is more compared to the major axis. And this is a spatial anisotropy, right? So because of the interactions of the particles inside in this region and the existence of pressure gradient, you will have, so this is at the initial stage at the level of the quark and gluons. So once this evolves to a more isotropic thing, so the effect of this initial geometry and the pressure gradient will be visible in your, let's say, spectra, or let's say the momentum anisotropy which we tell, and this can be quantified by taking the Fourier transform of the azimuthal distribution. So if we do that, the second coefficient V2 quantifies the elliptic flow, and this also tells us about the degree of thermalization in the initial state. So whatever is happening here, we do not have axis. The only axis is the charged particles which we measure. So if we do this measurement in data and extract this parameter, this will tell us about the amount of pressure gradient which existed in the initial state. So if you have a high value of V2, that means the system is thermalized more, the pressure is more due to let's say interaction between the particles, and therefore that is reflected in this coefficient. Now let us see how the coefficients behave as a function of transverse momentum. So this is for non-heavy particle, let's say kaon, pions, phi, protons, etc. So as you can see, the elliptic flow coefficient increases with Pt, and after certain Pt, let's say around when you reach 3 or 3.5, it sort of becomes starts to decrease, becomes saturated for some time, and then it starts to decrease, because as you know, the concept, once the pressure gradient diminishes, then that will be definitely seen here, but there are other reasons too. So if you concentrate on the low part, or let's say low PT part, which is the bulk part, you see the let's say mass hierarchy which we talked about in the first half of the lecture. And in the intermediate PT, you can see there is a distinct difference between baryons and mesons. So blue particles are all baryons, which is protons, lambda, cascade and omega, while the lower ones are mesons, which are your pions, kaons, phi and all that. And this is seen for, this distinctiveness is seen for all the centrality classes, while it is more distinct in semicentral collisions where the effect of flow is more. This is for the light hadrons, okay. So we see a presence of mass ordering and baryon-meson grouping. This is interesting. So what does it tell you? Now if you just divide the PT with number of constituent quarks, let's say in case of baryon it would be 3 and meson it will be 2, and similarly you also scale the y-axis, those are the elliptic flow coefficients with the same number, you see that the differences, let's say they diminished more or less in most of the part within error bars, they're agreeing or they lie on the same curve, but we also see there's a little bit difference still existing. So that is a clear signature. So this part, the bulk low PT part, is a clear signature of hydrodynamic evolution, but for the intermediate PT part, this absence of let's say the differences in baryon-meson grouping leads towards the let's say formation of particles via quark coalescence. So the idea is that in the intermediate PT, the hadron formation takes place by coalescing quarks, and so therefore 2 quarks combine to form mesons and 3 combine to form baryons, and therefore if you scale by the number of constituent quarks, you see a scaling. Although it is not completely proper, because in this region you also get contributions from, let's say, fragmentation and other mechanisms. So you see an approximate number of constituent quark scaling. Now let's see what is the scenario for heavy quarks. So you perform a similar measurement for heavy quarks like d mesons, and let's try to see what do we observe. So what we see, d meson flow increases significantly from central to semicentral collisions. Okay, so this is your central collision, so the collision is head on, and this is your, let's say, semicentral collision where you expect higher eccentricity. So as you see that the magnitudes are different, so you see higher flow for semicentral collisions compared to central collisions, and that is easy to understand because of the shape of the overlap region. And also for the low PT region, you are seeing the mass hierarchy observed in the low PT region. That is the VNs of d meson. The d mesons are heavier than protons and pions, and this hierarchy is still maintained for the low PT region, so that you can see that they take part in the, let's say, thermalization process, charm quarks. Although we do not expect them to take part in the thermalization process, but the data says because of this hierarchy which is observed, so, and this is a result of the hydrodynamic expansion, this also says that maybe charm quarks are also thermalized. And in the intermediate PT region, although the error bars are quite high, we can see that the d meson flow, where you see that baryon-meson grouping, you can see that the d meson flow is comparable to the flow of the pions. So this is a recent measurement where we measure flow, where CMS experiment has measured flow coming from prompt d mesons and d mesons from b hadron decays. So as here you can see that the blue points correspond to the prompt ones, while the red ones from b hadron decays, and you can see that the values for the prompt case are higher compared to the ones coming from the non-prompt. So this also suggests a mass hierarchy because these are coming from B quarks, so they are of higher mass. So in this region of PT, you see this mass hierarchy. So this was about the initial stages. Then let's see how we get information about the hot medium properties. So the golden observable is the nuclear modification factor. It's nothing but the ratio of the transverse momentum spectra observed in heavy ion collisions to that what we observe in PP collisions at same energies divided by the number of collisions. Okay, so that means you have scaled it appropriately. So had this nuclear collisions been similar to PP collisions, then you should observe RAA tending to 1. Okay. This part it is not 1 because in this region the scaling is not with respect to n number of collisions. Okay, so this is what it is expected, and any deviation from this binary collision scaling would refer to some final state effects. So let's calculate the RA of light flavors, then we'll go to heavy flavors. So you can see the red points are for central goal-goal collisions when there is a complete overlap, and blue points refer to let's say it is 70 to 80 or peripheral collisions, and green points are for p-led collisions where we don't expect a medium or strong medium to be formed. So here you can see that RAA is quite and it shows a strong centrality dependence, and the values of RA are lower compared to what you see in peripheral and what you see for lead-lead collisions where there is no medium, so there is no energy loss, so it is agreeing to the value of 1. While for the results of lead-lead collisions, the flavors or these hadrons, the quarks lose energy in the medium, and hence the values of RAA is less than 1, and this is even lesser for central collisions where the path length is more and the density of the medium formed is quite high. Now this was for light flavors. Now let's see the same for heavy flavors, whether they are losing energy or not. So what we see that the D mesons also show a strong centrality dependence. So red ones are for most central collisions. This is 30 to 50 peripheral, and this is p-led. So if you make a similar measurement of spectrum, transverse momentum spectra for heavy flavors and take the ratio with the same in pp collisions, so you also see whatever you have seen for light flavors. That means they also suffer energy loss while traversing through the medium, and it shows a strong centrality dependence, and you see nothing for the case of p-led collisions. That means the suppression what we see here is a manifestation of final state effects. Okay. So the story is suppression increases from peripheral to central collisions, it is clear. And the suppression observed in lead-lead collisions is due to final state effects induced by the medium. So now let us compare the RA of D mesons with light flavored ones. So red points are for pions, and this is for D mesons, and the green ones with huge error bars are for gypsy, which is like CC bar system. D mesons will have one heavy quark but another light quarks, and these pions and other charged particles are made up of light flavors. So what you see, there is a significant difference in the RAA. So the lighter ones for let's say low PT region, they lose more energy compared to, let's say, heavy flavor, or let's say D mesons, and D mesons lose more, or let's say charm quark lose more energy because gypsy has 2 charm quark and it has a charm and a light flavor quark, so therefore there is a significant difference in the RA. But if you just compare, the light flavors lose more than the heavy flavors. So this observation leads us to say that these signals are an interplay of the different QGP effects. It is how the energy loss is dependent on the type of quark flavor, and also quark mass dependence for in-medium energy loss. Okay. So gypsy has 2 quark, 2 heavy flavor quark, D meson has 1, and light flavors have not. And if you see non-prompt gypsy, so this is in a different rapidity thing, so for higher PT, so they lose also. But you can't compare, but the comparison is shown with comparison to, let's say, prompt gypsy and non-prompt gypsy. So prompt gypsy have, let's say they have CC bar, while the non-prompt comes from the beauty decay, so there's a difference in the RA. So it also shows the mass dependence of energy loss in the medium. So now this is a comparison where we show the energy loss of D mesons with DS mesons. Now the difference is DS meson has a charm quark and the other quark is a strange quark. So these have a light quark and a charm quark. So you can see that so we also see a strong suppression of ds reaching a minimum at pt around 10. So, and then we don't have measurement in this pt region. We can see there's a strong suppression, and there's also a centrality dependence. Here it is because it is like semi-central, so the medium, let's say path length will be different, so the Ra is higher than what we see here. And then here we compare with lambda C baryons. So now we have this particle species dependence because lambdas are baryons while others are mesons. So you can see a hierarchy here. So Ra of lambda baryon is greater than that of ds, and that is greater than of d. Okay. So that was all about open heavy flavor. Then let's see about what happens for quarkonia sector. So these are very interesting particles because they are bound states of QQ bar. So and in our case it is CC bar or BB bar. So why they are interesting? Because these bound states are formed because you know the production of QQ bar is described by perturbative QCD, but once they form bound state, that is very non-perturbative. So the formation of quarkonia state are like a lot of models, a lot of work is going to explain or the production cross section of them, but nevertheless they are formed very early in the collision, and this is the binding of the QQ bar state given by a Cornell potential. Now what happens if you put this state, because they have to go through QGP, so what happens if you put a bound state inside the QGP? Now QGP has deconfined color charges coming from other light quarks also. So if you put a bound state of QQ bar, let's say CC bar or BB bar in this deconfined medium, so you see that the confinement terms goes away, and this high density of color charges introduces a screening for this part of the potential, which can be parametrized like this. So in vacuum, when there is no medium, you have a J psi, which is let's say a CC bar state, and suppose, and depending upon the temperature and the binding energy of this state, we'll see that and the amount of debye screening which it gets from the other color charges, we'll see that at certain temperature this becomes less than the, let's say, radius, and then it now no more exists as a J psi particle, but it dissociates into a CC bar thing. Now if that happens, that is also, this was earlier termed as a smoking gun signature for the formation of QGP. So if this scenario is happening, that means the production, whatever you are measuring, the yield of J psi meson will be suppressed compared to their original production. Okay, so suppression of J psi meson was considered as a smoking gun signature for the formation of this medium. But there is another scenario for regeneration, maybe I'll come to that later, that now if you have sufficient CC bar quarks as produced in the deconfined medium, some of them also can join together to form bound states, so that can significantly enhance the J psi yield. So that is also known as regeneration of J psi. So these two competing processes go hand in hand, and both of these processes are signatures of formation of the presence of this medium. So one has to be very careful while interpreting the data. Then there is another thing, which is the sequential suppression of quarkonia. So this is a very interesting mechanism because you see you have different quarkonia states, J psi and its excitations like let's say chi c and psi, and if you see their masses and their binding energy, you can see that this is a very weakly bound state. So I have written as a decreasing order, and this is the size. Okay. So similarly for bottomnia state, you have this. So if you compare the binding energy, this is a very strongly bound state if you compare all 6 of them, and they have their respective let's say, size, radius and mass. Now if you put these states inside the medium, QGP medium, and this is the Debye screening, what you can see that let Tc be the deconfinement temperature. So this state would really survive. If you do a measurement, you will see the complete melting of these states by virtue of their small binding energy. So at a certain temperature, let's say at this value of temperature, your psi prime will go away because its binding energy is less. So depending upon the binding energy and the size at various degree of temperature, these states, they really dissociate. So you don't measure them. So there will be a suppression in the yield. This is known as sequential suppression of the resonance states of Charmonia or Bottomnia. And this should be observed in experimental measurement. Now this is melting versus regeneration, what I was talking about. So x-axis tells you the multiplicity density. So this is a measure of the, let's say, the centrality of the collision, and on y-axis you have the nuclear modification factor. So what you see here, let's concentrate on let's concentrate on the red points, which are lead-lead collisions at 5.02 TeV, and green points are for 2.76 TeV and gold 0.2 TeV. So there is an energy difference between all these measurements, and this is the RAA of inclusive GPSI. So what you see at lower energy, so as you go to higher multiplicity, there is a suppression of the, so RAA decreases. So there is a suppression in the yield measurement. But for these two energies, you see that as you go high in multiplicity, or let's say when your medium is let's say dense and strong enough, even the path length is more, you see a gradual increase in RAA, which will reflect the regeneration what I was talking about. So this is the Psi2S production measurement in lead-lead. As I mentioned earlier, the Psi2S melts by virtue of its low binding energy. So you should see a strong suppression of Psi2S compared to J-Psi, and this is what we are observing experimentally also. And this increasing trend of RAA towards low PT for Psi2S, and this is compatible with another measure, with a similar measurement from CMS. And this PT dependence is measured by these models, which incorporate both hydrodynamics, quark coalescence and fragmentation in their description of this thing. So this is the first measurement in LHC down to 0 PT. You see a significant suppression of Psi2S. So this is just to show that this is, let's say, J-Psi and this is Psi2S. This is just to show that transport models, which include recombination of charm quarks, describe the data well. Now let's, for sequential suppression, let's also see the case of upsilon. As we saw, upsilon 1, the binding energy is the highest. So it will, if you put this in medium, so you will see the yield or the upsilon state survives, while other excited states, they completely melt inside the medium. So this is just a schematic. Now let's see what the measurements tell us. So x-axis is n part, which is, let's say, the collision centrality. So this is the high central events, this is the peripheral events, and this is RAA. And what we see, the red points or the maroon points are upsilon 1s state, and blue points are upsilon 2s states, and we see that there's a strong suppression of upsilon 2s, which is expected. Now let's do an elliptic flow calculation of these states. And these are beauty, so these are quite heavier than charm quarks. So what we see that beauty V2 is compatible with charm V2 at high PT, and whether it can be explained by energy loss or path length dependence, we do not know yet, because the systematic the error bars are quite high, and these are all different theoretical models which would like to explain the data. And finally, we have the elliptic flow for, let's say, inclusive J-psi and upsilon, a comparison. So you can say that inclusive J-psi, which has CC bar configuration, it has a higher flow compared to upsilon. So beauty is not taking part in let's say flow, or it's not taking part in thermalization as per the data, but you should also see the error bars are too huge to make conclusions, and also if you see the centrality, it is quite inclusive, so you will also have contributions coming from central events. Now the third part is hadronization. We finished initial stages, then medium properties, then once they hadronize, how to probe them, and the best thing is to see their momentum, transverse momentum spectra. So here it's an interesting measurement of lambda C baryon and D0 meson at intermediate PT. So you see, if you take the ratios, if you see that there is an increase in the ratio at intermediate PT, and this is similar to what we have observed in light sector, where we saw that baryon to meson ratio increases in intermediate PT. This can be an after effect of the high radial flow, which really pushes the particles toward, let's say, higher PT, and we see the yield increasing. But we should, because of the error bars, one should be careful, and when you compare it with PP, the enhancement is quite significant for most central collisions in lead-lead. So this also shows a strong, let's say, strong signature towards the transverse flow which we see in lead-lead collisions. And this baryon to meson anomaly in charm sector, it was earlier observed in light flavor sector. You can see that increases from PP to central collisions, and this is compatible with theoretical models. You have this you see the comparisons with theoretical models, but they have huge uncertainties, and these models include both fragmentation and coalescence mechanism of hadronization. But with these error bars, it's very difficult to say what works at this sector now. So the take-home message is heavy ion collisions are to study the properties of strong interactions at high energy densities. So these results from GV and TeV energies have provided a lot of information which demonstrates a strong sensitivity to the properties of the medium. And the medium formed in such collisions has the characteristics foreseen for a quark-gluon plasma, behaves like a fluid, and has spectacular effect on hard probes, specifically on heavy flavors. And this vibrant experimental programs with precision measurements have been answering long-standing questions, driving heavy ion physics to multi-messenger era. So the thing is that these are very clean probes to study the medium, but they suffer from high statistics, but we have now new data with a lot of statistics that will give more precise measurement and information about the medium which is formed at high energy collisions. Thank you very much.